Hello, friends. We are talking about the white dwarf today. These dead stars were once thought to be sterile completely, but the new research suggests they could host surprisingly common, long lived habitable zones. So, today we are going to discover how planets could survive the star's red giant phase and find a new home in the faint glow of the white dwarf. Let's go. Hello, everyone, and welcome back to our cosmic journey. Today, we're diving into the question that might sound like science fiction, but is rapidly becoming a serious topic in astrobiology. Could we, or any life for that matter, live around a white dwarf star? For billions of years, life on Earth has thrived under the warm, steady glow of our sun. It is yellow dwarf star, stable and reliable. When we imagine other habitable world, we often picture them orbiting star much like sun, bright burning furnace that provide a constant source of energy. But what if I told you that some of the most unlikely places in the universe, which is similar to the remnant of the dead stars, might actually be surprisingly hospitable? This isn't just about the thought experiment. New research is revealing that the white dwarf stars, once considered the cosmic graveyard, could harbor remarkably common and long lived habitable zones. And the implications for the future of life in the universe are truly mind bending. To understand why this is such a surprising idea, we first need to understand what a white dwarf star actually is. Imagine our sun. It's currently in its prime, fusing hydrogen into helium in its core. It's what we call a main sequence star. But the stars, like everything else, have a life cycle. For stars roughly the size of our sun, this cycle is quite dramatic. In about 5 billion years from now, our sun will run out of hydrogen fuel in its core. When that happens, it won't just wink out. Instead, it will begin to swell dramatically, expanding into a red giant phase. It will grow so large that it will engulf Mercury, Venus, and possibly even Earth. The surface will cool down, giving it a reddish hue. This is a very different kind of a phase. It certainly doesn't sound like a good time for any life on the nearby planet. After this red giant phase, the star sheds its outer layers, forming what's known as the planetary nebula, a beautiful glowing shell of gas. What is left behind at the very center is the star's super dense core. This is our white dwarf. It's incredibly hot initially, but no longer undergoes any nuclear fusion reaction. Instead, it slowly and gradually cools down over trillions of years, essentially radiating away its leftover heat. For a long time, white dwarfs were considered cosmic relics, fascinating but ultimately barren. And for good reason. Think about the challenges. First, their size. A typical white dwarf is about the size of Earth, but it certainly has a mass of our sun that makes them incredibly dense. A teaspoon of white dwarf material would weigh tons. Secondly, their energy output, while initially very hot, they quickly dim compared to their main sequence predecessors. The habitable zones, which is a region around the star where temperatures are just right for liquid water to exist on a planet's surface, around a white dwarf is much closer to the star. We're talking about distance similar to Mercury's orbit around our sun, or even closer. Third, the red giant phase, it's remarkable. Any planet orbiting a star that swells into red giant would likely to be roasted or even swallowed entirely. How could life survive such cataclysm? These factors, made the idea of life around a white dwarf seem extremely remote. But science is all about challenging assumptions. The recent discoveries are forcing us to rethink everything. First hurdle to overcome is that the destructive red giant phase. If a planet is to be habitable around a white dwarf, it has to get three things right, and it has to get there somehow. There are few scenarios researchers are now considering, starting with possibility is that the planet, especially gas giant, could have pushed further out by the expanding stars strong stellar winds, surviving the red giant phase in a much wider orbit. Over time, as the star contract into a white dwarf, these planets might then migrate inwards again, or just find themselves in a new closer habitable zone. Another perhaps more likely scenario involves the formation of new planets or moons after the red giant. The planetary nebula that shed gas from the star contain a lot of material. It's plausible that the new smaller rocky bodies could collapse from their debris, eventually settling into orbit around the white dwarf. This is an exciting idea suggesting a second generation of planets. And finally, the existing rocky planet might simply survive, while Earth might be engulfed by our Sun's red giant phase. Planets orbiting slightly further out could endure as a scorched, airless husk. The question then becomes, can they, regain habitability? So let's assume a planet in, its planet orbiting around a white dwarf. What does its habitable zone look like? It is definitely different from our own because the white dwarfs are much fainter than our sun. Their habitable zones are much closer to the star. We are talking about distance ranging from few hundred thousands to few million kilometers, far closer than Mercury is to our sun. But here is a kicker. While the initial light from the white dwarf might be very blue and energetic, over vast timescales the light emitted become gentler, and crucially these habitable zones can be incredibly stable for billions of years. Remember, a white dwarf is just a slowly cooling body. It's not flaring or undergoing dramatic changes like younger stars. This stability is a huge advantage for the development of life as well as the evolution of life. Think about it. Our sun has about 5 billion years left on the main sequence. A white dwarf could provide a stable environment for life for 10 times that longer or even more. That's an immense amount of time for complex life to emerge and evolve. Now, living so close to the stellar remnant might sound dangerous. White dwarfs still emit significant amount of high energy radiation, particularly X-rays and UV light, especially when they are younger. They could strip away a planet's atmosphere or be lethal to the nascent life. So how could a planet in the white dwarf habitable zone protect itself? The answer is very similar to what we have on Earth, and likely lies with a robust atmosphere and a strong magnetic field. A thick atmosphere could absorb harmful radiation, just as our atmosphere protects us, and a powerful magnetic field generated by the molten core would deflect charged particles from the white dwarf, preventing atmospheric erosion. Interestingly, for a planet to remain volcanically active and maintain a molten core for billions of years, it might need to be larger than Earth. A super Earth like planet up to 10 times the mass of Earth could retain its internal heat for much longer, ensuring a protective magnetic field for eons. For life, life might need that kind of heat to evolve. For life as we know it, liquid water is essential. So, where would a white dwarf planet get its water? The process of star becoming a red giant and then white dwarf is incredibly destructive, and original water on the planet close in would likely be boiled away. This means that if the white dwarf planets are to be truly habitable, they probably need a new supply of water. The good news is that the white dwarf system are often surrounded by vast disks of rocky ice debris, the shattered remnant of the asteroid comets and perhaps even planet uh, that didn't survive the red giant phase. This debris can be seen as polluting the white dwarf's atmosphere, a clear sign that their systems are active environment. Over time, these icy asteroids and comets could be drawn in by the white dwarf's gravity, crashing into newly formed surviving planet and delivering the vital water needed for the ocean to form. This process, known as the late heavy bombardment or the secondary accretion, and is thought to have brought much of the Earth's water to our planet billions of years ago. So the mechanism is well understood. This is all theoretical, of course, but how would we actually find life or even habitable planets around a white dwarf? One of the most promising methods involves observing the white dwarf's atmosphere itself. As planets, asteroids, or comets fall into the white dwarf, their material is vaporized and become part of the star's atmosphere. By analyzing the light from the white dwarf, astronomers can detect the chemical fingerprints of elements like oxygen, carbon, and even water. Finding an excess of water or organic compounds in white dwarf's atmosphere could be a powerful clue that there are or once were watery, life-bearing bodies in the system. Another method involves looking for transiting planet. If the planet passes in front of a white dwarf from our perspective, it causes a tiny dip in the star's brightness. While white dwarfs are small, so are their habitable zones, making such transit more likely to be observed or probably observable. We could then analyze the planet's atmosphere for biosignatures, gases like oxygen, methane, or ozone that are often produced by living organisms. While no definitive white stars habitable planets have been confirmed yet, missions like the James Webb Space Telescopes are perfectly suited to make such observations. So, what does this mean for the future? If white dwarfs' habitable zones are indeed common and long lived, the implications are profound. First, it's vastly expand the potential for life in the universe. White dwarfs are incredibly numerous. Over 97% of all stars in our galaxy, including our sun, will eventually become a white dwarf. If even a small fraction of these can host habitable planet, then the number of potential abode for life in cosmos dramatically increases. Second, it offers a potentially long-term refuge for life. As our sun approaches its red giant phase, Earth will become habitable. But perhaps trillions of years from now, our distant descendants, if we are still around, might find a new home around the dim, stable glow of white dwarf elsewhere in the galaxy. It's a tantalizing thought, a way for life to persist far beyond the lifespan of its original star. It also suggests that the end of a star's life isn't necessarily the end for its planetary system or even life it might harbor. Instead, it could be a transformation, a cosmic recycling process that creates a new opportunity for life to emerge or to endure. Of course, it's not all smooth sailing. There are still significant challenges and open questions. Things like tidal locking. Planets so close to the white dwarf would likely be tidally locked, meaning one side always faces the star and the other side is in perpetual darkness. This could lead to extreme temperature differences requiring robust atmospheric circulation to distribute heat. Second, stellar flares. Especially in the early phase of the white dwarf, while the stable over long period, young white dwarfs can still experience occasional flaring, which could be dangerous to life or nearby planets. Third is the asteroid impact. The debris field that provides water could also pose a significant impact hazard. especially for newly forming planets. Next is observational limit. While the JWST is powerful detecting biosignatures on such faint planet and remains incredibly difficult task to look for such systems. Despite these challenges, the scientific community is increasingly optimistic. Each new discovery brings us closer to understanding these intriguing stellar remnants and their potential to host life. The notion that we could, or we would one day live around a white dwarf star truly pushes the boundaries of our imagination. It forces us to reconsider our assumptions about what makes a star habitable and where life can truly thrive. It's a testament to the incredible diversity and resilience of the universe. What once seemed like a cold, dead end for stars and their systems now appears to be a potential cradle for a new life, a beacon of hope in the distant cosmic future. So, as we continue to explore, observe, and theorize, the white dwarf habitable zones remain one of the most exciting frontiers in astrobiology. Perhaps one day future generation will gaze upon a dim Earth-sized star in their sky, knowing that life, against all odds, have found a way to endure. So, friends, what do you think? Would life survive and thrive around the white dwarf? Let me know your thoughts in the comments below. Don't forget to like this video, subscribe for more cosmic insight, and hit that notification bell so you don't miss out our next adventure. See you in the next one.